today our topic is differential equation. Okay, so a very important topic in mathematics. Mathematics plays a pivotal role in many scientific and engineering disciplines, and ODE is certainly an important branch of it. The subject of differential equations constitute a large and very important branch of modern mathematics, right? From the early days of calculus, the subject has been an area of great theoretical research and practical applications. And it continues to be so in our day. This much stated, several questions naturally arise. So the questions are, what is a differential equation? And what does it signify? Where and how do differential equations originate? And of what use are they? Confronted with differential equation, what does one do with it? How does one do it? And what are the results of such activity? So these are the questions came into our mind. So let us talk about some origin and applications of differential equation in the introduction part. So before you start a new thing, we have to know what is the origin and what is the historical development of the subject. Okay, so let us start with that. So you see, we are talking about the origin of the differential equation. So differential equation first came into existence with the invention of calculus by Newton and Leibniz. You may heard about that they are the most important physicist and mathematician, and they have invented the calculus, and with the development of calculus and mechanics, the subject differential equation came into the picture. You see, in chapter 2 of his 1671 work Methodus Fluxionum ad serierum infinitorum, Isaac Newton listed three kinds of differential equation. Number 1, dy dx equal to function of x. Number 2, dy dx is equal to function of x and y, and this is a partial derivative, x1 del y del x1, x2 del y del x2 equal to y. So these are the three kinds of differential equation Newton listed in his work, research work in chapter 2. Okay, in all these cases y is a known function of x. In all these cases y is a known function of x or of x1 x2, and f is a given function. He solved these examples and other using infinite series and discusses the non-uniqueness of solutions. Okay, so Newton first gave the idea of the differential equation. Later we will come to the definition of differential equation, don't worry. So next is a Bernoulli. Bernoulli proposed the Bernoulli's differential equation in 1695. Look at the year, it's 17th century, early in the 17th century. So Bernoulli, that is why there is a equation called Bernoulli's equation. We'll solve those equations, linear, but this is a non-linear. We'll explain everything. Historically, the problem of vibrating string such as that of musical instrument was studied by D'Alembert. Euler, you might have heard about Euler. It's a famous mathematician, Bernoulli, Daniel Bernoulli, and Lagrange, Joseph Louis Lagrange. These are the famous mathematicians, and they are dealing with the, actually in those time people are not only mathematician, they are philosopher, they were physicists, they are doing a lot of things, they beyond their knowledge. The problem of vibrating string was studied by these people, and they encountered with a differential equation. In 1746, D'Alembert discovered the one-dimensional wave equation. This is a very famous. In the higher level, you will study partial differential equation. In that case, you will study wave equation. And within 10 years, Euler discovered the, within 10 years, just only 10 years, Euler discovered the three-dimensional wave equation, right? The Euler-Lagrange equation was developed in the 1750s by Euler and Lagrange in connection with their studies to the tautochrone problem. It's a famous problem. Look at the year 1750. Euler and Lagrange. So these names are usually come into the picture if you study calculus, if you study applied mathematics, if you study differential equation, all this. This is the problem of determining a graph on which a weighted particle will fall to a fixed point in a fixed amount of time independent of the starting point. So this is the problem of tautochrone problem actually. And that was studied by Euler and Lagrange in 1750. Lagrange actually solved this problem in 1755. So look at that, the problem was in 1750 and the problem is solved after 5 years. So it takes years to calculate the problem, to analyze the problem, to find out the result of the problem and send to the solution to Euler. So Lagrange actually solved the problem in 1755 and sent the solution to Euler. Both further developed Lagrange's method and applied to mechanics and led to the formulation of Lagrangian mechanics. Okay. So later on you will study the mechanics, and that important part of that mechanics is the Lagrangian dynamics or mechanics. In 18th century, 1822, Fourier published his work as heat flow. Fourier. This is in Latin. So it means that the analytical theory of heat, in which he based his reasoning on Newton's law of cooling, namely that the flow of heat between two adjacent molecules is proportional to the extremely small difference of their temperatures. Content in this book was Fourier's proposal of his heat equation. Actually, that is the development of heat equation. Here you have observed that the development of the wave equation, there's a dealing with the wave equation, it's a partial differential equation, and here is the development of the heat equation, okay, of a conductive diffusion of heat. This partial differential equation is now taught to every student of mathematical physics and especially applied mathematics. So these are the short journey of historical journey of development of differential equation. And remember, people are solving differential equation of nearly 150 years. They are just solving differential equations to get the solutions. Okay, so this is the small journey of your historical development of differential equation, starting from Newton, Leibniz to Bernoulli. I'm talking about D'Alembert's wave equation, Euler, Lagrange's dynamics, and finally the Fourier heat equation. Okay, now the second question is, what are the applications? Why you are doing differential equation? Why you are solving differential equation? What are the major applications of differential equation? So the study of differential equation is a wide field in pure and applied mathematics, physics and engineering. All of these disciplines are concerned with the properties of differential equations of various types. Pure mathematics focuses on the existence and uniqueness of solutions. Okay, actually pure mathematics deals with the very local properties of the functions. So they are deal with the existence, uniqueness, solutions, function analysis, real analysis, complex analysis. The knowledge is required for that. While applied mathematics, if you're talking about applied mathematics, emphasizes the rigorous justifications of the methods of approximating solutions. Okay, so you see, differential equations is a wide field in pure and applied mathematics, physics and engineering. Not only that, we can add management, commerce, because cost function, the differential, share market, optimization, all these things are hot topics in the current world. So these peoples are also using differential equation. There is a differential equations of the cost function, marginal functions and all that. So there are a lot of applications in commerce, management and all that. So the differential equation is a vast application in all domain. So differential equation occur in connection with numerous problems that are encountered in the various branches of science and engineering. Okay, so let us see how. Let us see few sentences on that. The problem of determining the projection motion of a projectile, rocket, satellite, planet, these are all modeled in our differential equation. All model: projectile, motion of a projectile, motion of a rocket, motion of a satellite, motion of a planet, everything. There is a differential equation. The mathematical modeling is there, and for mathematical modeling you need a differential equation. So the problem of determining the charge or current in an electric circuit, that is also you need a differential equation. The problem of the conduction of heat, just only we talk about the heat equation by Fourier law of heat equation in a rod or in a slab. The problem of determining the vibration of a wire or membrane. The study of the reaction of chemicals, right? There are a lot of reactions in chemicals, and those can be described with the differential equation. The study of the rate of decomposition of radioactive substance or the rate of growth of population, that is also modeled in a differential equation. Suppose the current situation, in our current situation, that is the COVID-19 situation, pandemic, the growth of the coronavirus, that can be described by this differential equation. Actually, a lot of people in this world are currently studying the growth of the coronavirus and the population growth also. So these studies are required a modeling on that topic, and that modeling needs a differential equation. So this is the short description of the application. This is the least, but this is the last but not the least. There are so many applications in all over the world. You will learn as far you go through that. So it's a very important topic indeed. Let us now come to the next part. The very little differential equation is self-explanatory. It is an equation that involves differentials of functions. If I say one word, what is differential equation, or what do you mean by differential equation? It is a self-explanatory because it is an equation that involves differentials of functions. So before getting into the groove of our main discussion, let us first explain the term differential. What do you mean by differential of a function? Let us first describe that. So if fx is a function, if I write fx, okay, so fx is a function of independent variable, f is a function of independent variable x. And what do you mean by f dashed? F dashed x means its derivative of the function f, right? Then the differential of fx is written as dfx, right? You can write the differential of fx as dfx. Is defined by the relation, if you say is defined by the relation dfx is equal to f dash x into delta x. What is delta x? Delta x is the, capital delta x is the increment of x, right? Where delta x stands for the increment in x. Okay, so this is the differential. What do you mean by differential of fx? dfx is equal to f dash x delta x, where delta x is the increment of x. So in particular, suppose your fx is x, right? So in that case, what is your dfx? What is your f dash x? F dash x will be 1. In this case, your f dash x will be 1, right? So what will be your dfx? dfx will be 1 into delta x. That is, in this case, your increment and differential are same. Clear? So this is a particular case. So signifying the truth that for an independent variable x, the differential dx of x and its increment are the same. So in this case you can write, because your fx is x, so in this case you write dx equal to delta x. So in this case your differential and increment are the same. Okay. So for if y is a function of x, what we write? Y is a dependent variable, that is dependent on x. X is an independent variable, right? So you should write dy equal to dfx f dash x delta x. Okay, clear? Just already we discussed about this. And for dependent variable y equal to fx, the differential dy is proportional to the differential dx, and the proportionality constant being f dashed equals to dy dx. That is why we know that f dashed x is dy dx. Okay, so that is the concept of the differential. This is one reason why in elementary calculus the derivatives are called differential coefficient. There is a question, why the derivatives are called differential coefficient? So this is the concept of that, and this is the explanation of that before going into the detail of the differential equation. I hope this is clear to all of you. Let me move to the definition of differential equation and several other definition related to differential equation. Okay, now how will you define a differential equation? A differential equation is an equation connecting an independent variable x, a shout for function y equal to yx and its derivatives. Y prime is the first order derivative, y second prime, 2 primes are the second order derivative, and so yn is the nth order derivative, third order, fourth order, and so. That is an equation of the form. That is, a differential equation is an equation connecting an independent variable x and a function y is a y of x and its derivatives. Maybe it's a first order, second order, third order, nth order derivative. So we can say more compactly, a differential equation will be of this form. Will be of this form. This is the differential equation of this form, because f is a function of x, independent variable, a dependent variable y, first order derivative y prime, second order derivative y double prime, and yn maybe. So this relates the all functions of x, y, and derivatives. More or higher order derivatives are involved equal to 0. So this is called the differential equation. This is the more compact definition of differential equation. Okay. Now, why this differential equation called ordinary? Why this differential equation is called ordinary? If the shout for the function y equal to yx is a function of one independent variable x, if we are talking about one independent variable x, the differential equation is called ordinary. Okay, this is an ordinary differential equation because there is only one independent variable x is involved. So that is why we say ODE, ordinary differential equation. Okay, this is called ODE, ordinary differential equation. And look at that, some examples of ordinary differential equations are dy dx plus xy equal to 0. This is equation 1. And d2y dx2 minus 8x dy dx plus y equal to 5. 2 d2y dx2 plus dy dx plus x equals to cos x. 3. And number 4, x square minus y square into dx minus x plus y into dy. Number 5, d2x dt2 whole square plus omega square x cube equal to 0. Number 6, 1 plus d2y dx2 whole to the power 3 by 2 equal to a d2y dx2. Number 7, y equal to x dy dx plus c dx dy. So all these are the differential equations, ordinary differential equations. We are talking about a ordinary differential equation. Okay, let's move to the next part. When the south for the function y is a function of two or more independent variables, if we are talking about two or more independent variables, for example, suppose y is a function of x and t. Suppose if you are talking about a rectangle, right? So area of the rectangle depends on the length and breadth. So area is a function of length and breadth, right? So this is how it's a length and breadth, it depends on. So this is how it depends on multiple independent variable, more than one. So if there is a more than one independent variable, then we call this type of different. In that case, you cannot use the total derivative symbol. You have to use the symbol del. Del. This is called del operator. Del del x. You have to write del del x or del del y. Right. This is called del operator, and this is the partial differentiation operator. So look at that. You have a partial. In that case, it is called partial differential equation. Okay. So more than one independent variable. Here x and t are the independent variable. Okay. For example, look at one. This is your del u del t plus lambda del 2u del x2. This is a second order partial differential equation. I will define the order and degree just after this. So this is x and t are the independent variable and u is a dependent variable. So u can be written as u is a function of x and t. In this case also, look at that, u and rho are the dependent variable. So u is a function of x and y. U is a function of x and y, and rho is also a function of x and y. Okay. So this is how your partial differential equations are. Examples of partial differential equation. So the conclusion is that if your differential equation having only one single independent variable, that is called ordinary differential equation, and if it is a more than one independent variable, that is called partial differential equation. So more than one independent variables are involved, those are called partial differential equation. If only one independent variable involved, that is called an ordinary differential equation. Okay. Next, we'll define a most important part of differential equation, that is the order of the differential equation. So what is the order of the differential equation? The order of a differential equation is the highest order derivative involved in the equation. Is the order of the highest order derivative involved in the equation, that is called the order of the differential equation. Okay. So in your differential equation, let's go to the examples. In 1, what is the highest order derivative involved in equation 1? 1. You see first order derivative only involved. You see only first order derivative. So this is a first order differential equation. This is a first order differential equation. Okay. Let me write here first order. Okay, just like this. So this is a first order differential equation. What about this one? This is a highest order. What is the highest order derivative involved in this equation? Say 2, second order. So this is a second order. This is a second order differential equation. What about the third one? This is also second order. Okay. What about the fourth equation? This is a first order. So let me write second here. Second order. And the fourth one is the first order. Again, you see dy dx, if you simplify this equation, because it is written in the differential form. And what about the fifth one? d2x dt2. Here t is the independent variable and x is the dependent variable. So what is the order of the fifth one? Second order. Here also you have d2x dt2, second order. So order of the differential equation is second order. What about the sixth one? It is also of second order. d2y dx2 is involved. What about the seventh equation? It is also dy dx. So first order derivatives is involved, so it is called the first order differential equation. So in this case you have to write first order ODE, ordinary differential equation. So this is about your order of the differential equation. Let me now talk about the degree of the differential equation. What is the degree of the differential equation? This is also very important in differential equation. The degree of a differential equation is the power of the highest order derivative involved in the equation after it has been made rational and integral as far as derivatives are concerned. So what is the degree of the differential equation? It is the power of the highest order derivative involved in the equation. Power of the highest order derivative involved in the equation. And if the equation is not in rational form and integral form, you have to make it rational and integral, otherwise you cannot specify the degree. For example, let us see. So what is the power of the highest order in equation 1? 1. Power is 1. So it is a first order first degree equation. The name of the equation is first order first degree. What about this one? This is a second order differential equation. But what is the degree? The power of the second order derivative is 1. So it is a second order first degree. Okay, so this is a second order first degree differential equation. This is also third one. Look at the third one. The order of the derivative is 2. Fantastic, because it's a second order derivative. But what is the power of the first order, second order? What is the power? Power is 1. So in this case also you have second order first degree. And what about this? This is your first order first degree again, because you have dy dx, no power. And what about this one? This one, the power is 2. So this is your second order second degree. Okay, this is your second order second degree differential equation. Okay, so this is your second order second degree differential equation. And what about 6.1? You have mentioned that order of this differential equation is second, but second order, this is a second order differential equation, but you cannot specify the degree because you have a fraction in the power. So let us write this differential equation in that form. Let us square both sides. 1 plus, I am writing d2y dx2, look at that, I am writing 6 whole cube. If you square both sides, squaring both sides, then it will have a square d2y dx2, right? And this is your whole square. So now you can tell me the power. What is the power of the highest order? If you expand this is a cubic expansion. If you expand this, you will get a 3 as a power of this highest order. So it is a second order third degree differential equation. Okay, so look at that. That is why in definition of degree it is written that after it has been made rational and integral. Okay, otherwise you cannot specify the degree. So this is the second order third degree. This is a second order third degree differential equation. And this is, what is the degree of seventh? You have to arrange seventh also, because this is, you have dy dx and here you have dx dy. Let me write that. So I am writing y equal to x dy dx. It can be written as, and you can write dx dy as 1 by dy dx. So if you simplify, you will get dy dx whole square plus c and y into dy dx, right? Okay, let me write in a more clear format. So it is written in the form of dy dx. Now you can specify the degree. The degree of this differential equation is 2, because you have a first order derivative involved and power of the highest order is 2. So it is a first order second degree, right? Okay, so this is all about your order and degree, a very important concept of differential equation. Let us now move on to the more concept. Now the question is, what is the linear? Because people are talking about linear and non-linear, and if you see in the world, in your practical life, in your environment, or whatever problem you will solve in later on, suppose in higher studies or in your research work, all the problems are non-linear actually. But what is the linear? What do you mean by linear differential equation? An ordinary differential equation order n is said to be linear if it assumes the general form. There is a general linear form of this. This is the linear differential equation of nth degree, nth order, sorry, nth order linear differential equation. This is the example of an nth order linear differential equation. Okay, so what is the form? You look at that. Highest order derivative involved in dny dxn, nth order, and a0x, a1x, ana, these are all coefficients, functions of x. Bx, these are all functions of x. There is no function of y. All are functions of x. The coefficients are all are functions of x, and a0 not equal to 0. This coefficient of the leading term is not equal to 0. Okay, the coefficient of the leading term is not equal to 0. So the highest order derivative is nth order, and look at that, the degree of the highest order is 1. No other derivative has degree more than 1. You have no derivative have degree more than 1. All the derivatives are of degree 1, and y power is also 1. Power of y is also 1. You look at that, power of y is also 1. So this is an example of a general equation, general form of a linear differential equation, general form. So let me just explain this one. How will you identify the linear differential equation? That is a big question. First, the highest possible degree of y and its derivative is unity. Clear? Just already I spoke about that. Already I gave you the example. And the highest possible degree of y. Y is a dependent variable and its derivative. Okay? And x is the independent variable. Number 2, product of y and any of its derivative do not appear in the equation. Be careful. There should not be any product of y and derivative in the differential equation. Y and its derivative do not appear in the differential equation. Otherwise, it will be non-linear. So here in the example, you see there is no product of y and its derivative. It's a product of function of x and its derivative. Product of function of x and y. So product of derivatives and function of x, only function of x. Number 3, no term involving transcendental functions of y and its derivative is included. Okay, there should not be any term involving transcendental functions of y. So sine y, cos y, these are not trigonometric functions, these are called transcendental, and these are non-linearity is actually there. If you have a sine y, cos y, so suppose sine y, what is the expansion of sine y? Expansion of sine y is y minus y cube by factorial 3 and plus y5 by factorial 5 and so on. So there is a non-linearity. You see, y has power more than 1. So this is the non-linearity. So if any equation having a transcendental functions, that is a non-linear. Clear? So there are 3 points you have to keep in mind if you are talking about a linear. What is a linear differential equation? The highest possible degree of y and its derivative is unity. Products of y and its derivative do not appear in the equation. No term involving transcendental functions of y and its derivatives is included. Okay, so these are the 3 important points. Let us now have some examples on that. Let us find out which one of them are linear and which one of them are non-linear. Okay, so first one. What about first one? So you see, first one is it's a function of x, coefficients are function of x or constant, maybe constant, and you have a derivative, second order. Okay, it's a second order derivative, highest order derivative is second order, and all the dependent variable and derivative dependent variable is y, so power is 1, and power of degree of derivatives are 1 also. So it satisfies all the 3 conditions. Highest possible degree of y and its derivative is unity. product of y and its derivative is not appeared in equation 1, and no transcendental functions. So this is called second order linear ordinary differential equation. What we say? Second order. Let me write second order linear ODE, ordinary differential equation. Clear? So this is your second order linear ODE. What about second one? Second one, you see, you have a third order derivative, and the coefficients of the derivatives are all constants, 1, 3, 3, and coefficient of y is 1, and you have a function of x, transcendental function, but that is on independent variable cos x. So it's all our functions of x are constant, and it satisfies all the three conditions of linear. So this is called third order linear, what is called third order linear ODE, ordinary differential equation. Third order linear ODE, right? And let's come to the number 3. What about number 3? Yeah, this is not linear. Why? Because you have a y square. And it doesn't satisfy the conditions of a linear, because y power is not unity, its power is 2. It's a non-linear term. So this is a first non-linear first order ODE. What we call non-linear first order nonlinear first order ODE. Okay, so this is the nonlinear term. Now let's come to the next one, fourth one. The coefficients are all functions of x. Look at that, the functions of x, coefficient of y is function of x, and dy derivative is 1. So it is a first order, again it is a first order linear ODE. Let me write, it's a first order linear ordinary differential equation. Okay, this is a first order linear ordinary differential equation. What about fifth one? X plus y whole square. So you have a dependent variable y, and its power will be, if you expand, its power will be 2. So that is a nonlinear term, and there will be product with this differential dependent variable and its dy dx. So it is a nonlinear first order nonlinear. Okay, so this is a nonlinear differential equation, ODE, ordinary differential equation. What about the sixth one? This is also nonlinear, because you look at that, you have a d2y dx2 whole to the power 5. So this is not linear. Okay, this is a highest order derivative is fourth order. So it is a fourth order ordinary differential nonlinear fourth order ODE. So you can write nonlinear NL. For nonlinear I am writing NL, nonlinear fourth order ODE. Okay, and come to the seventh one. What about the seventh, equation 7? So this is also d2y dx2, but you have a product of, you have a transcendental function sin y. You have a sin y. So this is also sin y is also a nonlinear term, because I have explained that expansion of sin y is this. So if you have a sin y, that is a nonlinear in the dependent variable. If it would have sin x instead of sin y, that in that case it will be linear, but you have a sin y, so this is a nonlinear, right? So we can say this is nonlinear, and it is a second order nonlinear second order ODE, second order ODE. Okay, and the last one. What about last one? Last one, you see, sixth order derivative, highest order derivative is sixth order, and you have a product of the derivatives. You have a product of the derivative. In this case you have a sin y as a nonlinear term. In this case I have a fifth degree, it cannot be fifth degree, so it's violating the conditions of the linearity, so it is a nonlinear term. So this is a nonlinear sixth order ODE, because the product of this is actually nonlinear term. So this is called nonlinear. If I say this is nonlinear sixth order ODE. So this is all about your linear differential equation, and previously it was order, degree, what is ODE, what is PD. So this is the basic introduction of differential equation, and a lot of important definitions, examples also. Let us come to the last section of your topic today, formulation of differential equation, its significance. Okay, so why are you going to formulate the differential equation? That is a big question. Why I am doing the formulation? Let us have a beautiful example, very easy example for you actually. So you see, you have learned in your school level the equation to a straight line in the xy plane. How will you write the equation of a straight line in a xy plane? So if you draw the straight line in this form, so this is the straight line, right? This is called the intercept form. This is a x by a plus y by b equal to 1, right? Or you can say this is a intercept form, or you can put in the normal form x cos alpha plus y sin alpha equal to p, if p is the perpendicular distance from the origin. Okay, and or the equation can be written in the more symmetrical form x minus x1 by cos theta, y minus y1 by sin theta, that you have learned in your school level. Or slope intercept form, that is y equal to mx plus c, that is y equal to mx plus c form. Okay, so m is the slope and c is the intercept. This is called the slope intercept form. Okay, so these are the forms, and also there are some 2-point form, x minus x1 by x2 minus x1 equal to y2 minus 1. That is also a fifth one. Yes, you have a fifth one, I missed it. So you have a fifth equation also. So these are the form of a straight line in the xy plane I am talking about. Okay, so let us now, surprisingly all the forms ultimately involve two arbitrary constants. You look at that in all the forms. What are the arbitrary constant in the first form? A, B. What are the arbitrary constant in the second form? Alpha and P. What are the constants? Are in this case also you have 2, and in this case also you have 2 arbitrary constants, M and C. These are actually parameters. For the sake of simplicity, I am just considering this one, D. That is the slope intercept form. Okay, let us take that y equal to mx plus c. Let me take this form. So let us differentiate this first order derivative dy dx. What you have, m and c are the parameters, so you have m. Again differentiation, let me differentiate again. What you have, equal to 0. So that is the differential equation of a straight line. That is the differential equation of the family of straight line of the slope intercept form. Actually, how many straight lines are there? If you write y equal to mx plus c, how many straight lines are there? The question is that infinite. Because if you change the values of m and c, there will be infinite number of straight lines. So this represents the family of straight lines. And what about this? This represents the family of, this represents the differential equation of the family of straight lines. This represents the differential equation. Let me write that thing. Differential equation of the family of straight lines. Family of straight lines. Okay. So this represents the differential equation of the family of straight lines. And what you understand from this relation, that which effectively shows that any straight line is characterized by zero curvature. So actually it denotes the curvature of a line, curvature of a curve. It may be. So what is a straight line? Straight line is like this. There is no curvature. So it's a zero curvature. Its curvature is represented by 0. So that proves by the differential equation, and its differential equation represented by this. So that is the significance of the formulation. Why I am doing the formulation of the differential equation? This is the significance. Clear all of you? Let me give you more example on that. One more example. So differential equation of a family of curves always brings light to the intrinsic features of the family, either directly or indirectly. So this is an intrinsic feature. Okay. Now consider the family of unit circle. A circle x minus a whole square, unit circle, its a radius is 1. So its a circle is like this. Its center is AB. So okay. And you know how to eliminate a and b. There are two parameters a and b. So if you eliminate a and b, you will get this differential equation. Eliminating a and b, just like the differential I have solved by the differentiation first order, second order. So if you differentiate once, you will get 2 into x minus a plus 2 into y minus b into y1 equal to 0. If you differentiate again and eliminate a and b, you will get this type of differential equation. And this proves that this is the measure of the curvature. This is the measure of the curvature, and right hand side is a 1. So it shows that curvature of the family is constant. So it claims that constancy of curvature for circle, because circle has a curvature as a constant. So it proves that constancy of curvature of circle. So this is the physical significance of the differential equation, and it shows the light the intrinsic feature of the family either directly or indirectly. Clear? Now what you will do with this form? Can you get the solution of d2y dx2 directly from this? Yes, I can get the solution y equal to mx plus c from this differential equation. How? Let me write d dx of dy dx equal to 0. If I write this differential equation in this form, this is the form. If you integrate once, you will get dy dx equal to constant c1. If you integrate once again, you will get, if you write in the differential, if you integrate once again, you will get what you will get? You will get here y equal to c1x plus c2. So this is the straight line, that straight line I was talking about. So from the curve, eliminating the parameters, you are getting the differential equation, and by solving the differential equation, you will get the curve. And look at that, if you have two parameters, the order of the differential equation will be 2, and if you have a single parameter, order of the differential equation will be 1. Okay. So second order differential, 2 parameters, that means the order of the differential equation will be 2. So let me now give one example how to get the form of the differential equation. Let us have an example, a very important example. Application is very, very important, because I have solved in a different way, different manner. Find the differential equation of the family of curves given by y minus x square equal to a e to the power x plus b e to the power minus x, where a and b are the parameters of the family. Okay. So what we will do, you will first differentiate. So let us differentiate, successive differentiation, because you have two parameters. So your differential equation must be of order 2, remember. Okay. And if you get the solution of the differential equation, it will have 2 arbitrary constant, that is vice versa. So our successive differentiation of the above equation will we get these two subsidiary equation 1.2, that is dy dx minus 2x, this, and equation 1.3, that is d2y dx2 minus 2 equal to a e to the power x plus b e to the power minus x. Clear? So these three relations, look at the relations. What you have in these three relations involving a and b. These three relations are involving a and b, the parameters. So if you want to eliminate the parameter, you can write in this determinant form. Just like you consider this as a homogeneous system of 3 linear inhomogeneous equations in 2 unknowns a and b. Just consider them as a system of 3 linear inhomogeneous equations in 2 unknowns a and b. And from the theory of vector spaces, it follows that the system of equations have infinitely many solution if their determinant is 0. Infinitely many solution if their determinant is 0. So you can write in this determinant form, and if you expand you will get the ODE. So this is the easiest way to find out the differential equation of the family involving this type of problem. So I have explained a very important problem. Let me now give you a very important concept regarding this. Yes, this is the last section of my topic today. Classification of solutions. So the solution which contains a number of arbitrary constants equal to the order of the differential equation considered is called a general solution, or primitive, or complete integral. There are three names. So a solution of the differential equation which contains a number of arbitrary constants equal to the order of the differential equation considered. If you consider the second order differential equation, your number of arbitrary constants will be 2. Just already we talked about that. We explained that. And that is called the general solution, or primitive, or complete integral. Okay. So solutions obtained from the general solution by assigning particular values of the arbitrary constants are called the particular solutions. So if you have a general solution and you are substituting the values of x and y, suppose x equal to 1, y equal to 1, that means you can get the values of the arbitrary constants by substituting the values. This type of solutions are called the particular solutions. That means you are getting particular values to the arbitrary constants. That is why you are getting a particular solution. Okay. And for some differential equation, there exist solutions that involve neither any arbitrary constant nor they can be identified as particular solutions. These solutions are called singular solutions. We will explain singular solutions later on more elaborately. Before that, just try to understand that if it is not a general solution and not a particular solution, those type of solutions are called singular solution. Now there is a questions for all of you. All of my students, please answer this question. Find the order of the differential equation whose general solution is given by this: y equal to c1 plus c2 cos of x plus c3 c4 e to the power x plus c5, where c1 c2 c3 c4 c5 are arbitrary constant. So you have to mention the order of the differential equation. So you can see how many arbitrary constants are there. 5. So the question is, if I put a MCQ, the option will be 5, 4, third option will be 3, and the last option will be 2. So let me find out. Now the question is, these 5 constants are independent or they are dependent. Look at carefully the equation. You can write the equation in that form. How? You can write that equation in the form of c1 cos, because cos of a plus b is cos a cos b plus sin a sin b. So you can write c1 cos c3 plus c2 cos c3 into cos x. X is the variable, these are the constants, minus, because cos a plus b is cos a cos b minus sin a sin b. So there will be minus c1 sin c3 plus c2 sin c3 into sin x. Okay, minus c4 e to the power c5 into e to the power x. Okay. So this is how you can write the equation rewrite the equation in this form. So if I write this constant as a, this constant as b, and this constant, this is also constant. Look at that, c. Then what you have? You have a cos c, a cos x, sorry, minus b sin x minus c e to the power x, plus, na, there will be there. Okay, there is a minus. Okay, So this is a minus. So how many constant now? How many arbitrary constant now? A, B, C. And these are independent. But previously the 5 arbitrary constants were not independent. Okay, so be careful about that. So you have, lastly you have a independent arbitrary constants. So the order of the differential equation will be 3, because you have 3 independent arbitrary constants. So that is why the order of the differential equation will be 3. In that case, in the previous case, the arbitrary constants were not independent, but they were dependent. Okay, dear students, so this is my lecture today. I am finishing up here. Tomorrow I will do equations of first order, first degree. This is the introduction class. So I hope this is